Good afternoon, friends. So today we will be discussing on co-seismic and interseismic land surface displacement monitoring by Spaceborne DInSAR technique. Myself, Dr. R.S. Chatterjee. Okay, so today what we will discuss, it is the co-seismic and interseismic land surface deformation, or this how the strain is getting accumulated in the crust. Basically, we will study earthquake and the stress strain this related to earthquake that will be studied by Spaceborne geodetic techniques. Earthquake is basically caused by a sudden rupture or break of the earth crust. Here the elastic rebound theory is one explanation of how earthquake occurs. Okay, in the rocks the stress gets built up in the rocks of the earth crust, and as the stress is getting building up, so there is strain is accumulated. Okay, as the strain is accumulated, finally it reached this yield strength of the rock. Okay, and then this rock needs to release the stress, and when it releases the stress, so it will bounce back without any permanent deformation. But this is as long as it is strained elastically. Normally the rocks can accommodate only a small fraction, generally 1 to 2% as elastic strain, and beyond this limit there is permanent damage takes place or rupture occurs in the rock. Okay, so when the rocks breaks or when the rock ruptures and when this earthquake occurs, so some of the energy goes into breaking the rock and a lot of energy goes into the differential motion of the rocks. Sometimes this rupture or this fault, it may not reach to the surface. In generally, it reaches the surface, but sometimes it so happen that it does not reach to the surface, and in such cases, it remains buried under the surface, and then it is known as the blind fault. So, when the rock ruptures and earthquake occurs, so the stress is released. Okay, and when the stress is released with a high magnitude earthquake, the rocks in the earth crust again it starts getting accumulated stress and strain. So this elastic rebound theory, which is one explanation of this earthquake and earthquake deformation cycle. So here basically how this elastic rebound theory, it explains earthquake is something like this. In the illustration on the right side you see, the first one is left top, you see this is the undeformed this block of rock. Okay, and in the middle of that you can see this there is the potential this fault plane. This is the trace of the fault. Okay, and this stress is applied on the either side. Basically shearing stress is applied on the top side and the bottom side. Okay, by the arrow you can see that in the right side you can see how the stress is applied, and to see how the rock is getting strained we have put this thing your fence, and what kind of deformation is taking place. So you can see here this stress is applied, and in the left side towards the top and the right side towards the bottom, and while the stress is applied, what happens is rocks get strained. Okay, rocks gets deformed, and which you can see in this fence as well, and fence gets curved, and finally when the rocks gets and it reaches at at the yield strength, then what happens, these rocks ruptures, and you see at that particular position when the rock ruptures, you see that rock is still strained, but after this rupture, it breaks into two blocks, the left side and right side blocks. So then these two blocks are getting displaced, and it is a kind of strike slip fault. You can see this. So this is basically dextral strike slip faulting. Okay, so after this earthquake occurs, then immediately after that you can see that on the right bottom the rocks rebound to the original undeformed shape, and then again the rocks is undergoing this is subjected to stress, and again as the rocks is getting stressed, then again the strain will be accumulated and the cycle will continue. So this is how elastic rebound theory this explains this earthquake and this stress strain deformation cycle associated with an earthquake. So an earthquake and the seismic waves. So here you see an earthquake is caused by sudden movement on a subsurface fault, okay, and the energy is released. So basically this energy which was stored as strain due to the applied stress, so this energy is converted to seismic waves, and the seismic waves radiate from the earthquake focus, and we need to know what is the focus. Focus is basically the origin of the earthquake, okay. So these seismic waves, this cause ground shaking, and the seismic waves, because of this ground shaking, their damage takes place, okay. And these seismic waves can be measured using seismometers. So on the right side illustration, you can see there is E, N, and Z. It's basically there are three components of a seismometer which records the P and S waves from a local aftershock related to this Kilari Latur earthquake in India 1993, and it is at a hypocentral distance of 5.3 kilometers. Okay, so this you can see how seismometer measures the seismic waves. Now this focus and epicenter, as I have already told you, the focus basically the origin of the earthquake. So this is the starting point of an earthquake below ground where faulting occurs. Okay, this is also known as the hypocenter, and the point is directly above the focus, and on the ground is the epicenter. So earthquakes are generally the strongest, okay, at the epicenter, and becomes gradually weaker on either side, okay, further away on both sides. In general, it happens, but it is not happening always. That we will see in some of the examples later on, okay. So this is all about focus and epicenter. So in and around the epicenter, in general, there are maximum, this earthquake is very, very strong, and the maximum damage takes place. And as you go away from this epicenter, this damage gets reduced, okay, and the strength of the earthquake also gets reduced. Now coming to the magnitude and intensity of an earthquake. So earthquakes are measured based on three different scales, okay. In the first this scale, it measures the actual size or magnitude of the earthquake, okay. In the second scale, it measures the effects of or the damage of the earthquake, and in the third, it measures the total energy of the earthquake, okay. So a seismogram, that is a seismograph, basically the name of the instrument. So the seismograph is used to measure the strength of an earthquake, and it produces seismogram. So the seismograph produces a seismogram which shows the amplitude of the earthquake. The amplitude of the earthquake, as obtained from the seismogram, is translated into 1 to 10 scale, and on the Richter scale, and each step from 1 to 2 or 2 to 3 or 3 to 4. And each scale, each step of the scale, okay, it represents a 10-fold increase, okay. So basically 1 to 2 or 2 to 3 or 3 to 4, it is not just 1, but it is a 10-fold increase from 2 to 3 or from 3 to 4, okay. So in the size of the earthquake. Now nowadays, the magnitude of an earthquake is most scientifically measured by the moment magnitude. And the scientists mostly prefer this moment magnitude scale than the Richter scale. Why? Because it is not based on instrumental recording of an earthquake, but it is based on the area of the fault that ruptured in the quake, okay, and it is calculated by multiplying the area of the fault's rupture surface with the slip of the fault, and it is calculated. On the right side, you can see this formula. So this is the magnitude m naught t. Okay, the seismic moment. So moment magnitude is equal to the mu is multiplied by s, and the delta mu t. Basically, this is the rigidity area and the slip of the earthquake. Now, the effects of an earthquake, or this damage, what it does, an earthquake does. So that is measured in terms of effect of the earthquake. So the effect of an earthquake on the surface of the earth is called the intensity of the earthquake, and the intensity scale consists of a series of certain key responses, such as when the earthquake is very, very feeble, okay, when it is very, very weak, sometimes people may not even can feel it, okay, and then sometimes people awakening this earthquake means a little more, so one can understand. Then this earthquake maybe is a movement of furniture, so furniture gets moved, okay. So like clocks, and now like doors, like window pane, Okay, so this kind of movements can be observed, shaking of these, and then sometimes damage to the chimneys, and finally total destruction. So this scale is 1 to 12 scale, and this scale is known as the Mercalli scale. It measures the earthquake's effect on a scale of 1 to 12. But this scale is very, very subjective. The modified Mercalli intensity scale, so it is MMI scale also it is known as. So here the value assigned to a specific site after an earthquake, okay, and it is a more meaningful measure, particularly in terms of severity of the earthquake, and it is to the non-scientist, it has some meaning that they understand what is the effect of the earthquake, okay, whereas in case of this thing, your magnitude on the moment measure and in the intensity, so it is, in the moment measure and Richter scale, so it is the strength of the earthquake, whereas in case of intensity, it is the, what is the effect of the earthquake, and this effect is 1 to 12 in Roman scale. Okay, one is only detected by seismographs, but this human being cannot detect it, only by instrument, okay. And if you, as you go gradually up, 1, 2, 3, 4, 5, like this, and slowly the earthquake, your effect is increasing, and in 6, it is felt by all, and but the damage is not substantial, the very little damage, and in case of 12, it is a total destruction. So it is all. And now coming to the plate tectonics theory. Plate tectonics theory is very, very important to understand earthquakes. In fact, there are 7 major your lithospheric plates. The entire lithosphere is divided into your segments or these plates, and these are known as lithospheric plates. Some are major plates. There are 7 major plates, and there are some minor lithospheric plates. The major lithospheric plates like Indo-Australian plate, Eurasian plate, African plate, North American, South American plates, Pacific and Antarctic plate. So now you can see in the illustration below that, for example, in your Indian plate, that's on the right side, you can see Indian plate. Okay, so that is moving mostly towards north, a little bit towards from north to northeast. Okay, whereas the African plate is moving. This differential movement is mostly towards northeast. And you see these South American and North American plates, it is moving towards west, and the other plates you can see the movement is shown by the direction of the arrows, and the length of the arrow, it indicates the magnitude of the movement. It is shown in the figure inside. Okay, like the Indian plate or the Indo-Australian plate, it is moving around 5 to 5.5 centimeter per year. So this is shown by the length of the arrow. Okay. Now, this in this plate tectonic theory, so you can see that at the boundary of the plates, and if we compare with these occurrences of the earthquake, we see that the geographic locations of the earthquakes, they coincide with the plate boundaries. Okay, and we see these thousands of small earthquakes occur almost every day, and you see in the illustration, it is shown in in 2 colors. This one is S is shallow and M is intermediate depth earthquakes. But if you see the pattern of the earthquake occurrences, so you can see there are certain lines you can see, and these lines basically it is coinciding with the boundaries of the plates. Okay, some are shallow and some are your intermediate, and some are deep. These your earthquakes, but essentially this almost all the earthquakes all along the plate boundaries. Okay, and what is observed that what I was telling you, that there are thousands of small earthquakes occurring almost every day, and medium to large earthquakes, that means this moment magnitude 6 to 7 that occur almost once a month, whereas strong earthquakes where the magnitude is more than 8, it occurs once in a year in general. So, and there is the shallow earthquake, the intermediate earthquake, and deep earthquakes, they occur at different kind of plate boundaries. In general, the deeper earthquakes occur in the convergent plate boundary or in the subduction zones. Now coming to the different kind of plate boundaries, there are essentially 3 types of plate boundaries. There are convergent plate boundary, divergent and tensile faults. Okay, convergent plate boundary also known as the subduction zone. Okay, where this one plate is going under the another plate. So this is also known as this is the where the earth crust is destroyed. So it is also known as the subduction zone, and in general, this subduction zone is the source of the large earthquakes, and these large earthquakes are generally, these are deeper in general. Okay, As we go to the divergent plate boundary, you go down to the right bottom. So this is the divergent plate boundary. If you see this cartoon, and in this cartoon you see that this is the spreading ridges. So here the two plates are going away from each other, and here the earth crust is created in between. And here this is the source of the small earthquakes, and these small earthquakes are generally all are shallow earthquakes. Okay, and on the this left bottom you see this is the transform fault. This cartoon here you see that these two plates slide past each other, and this is a kind of this conserved plate boundary. This is earth crust is neither created nor destroyed, and it gets remains conserved. And in the transform fault, this is generally the source of medium to large earthquake. And in the left top illustration, you can see that different kind of plate boundaries. It is shown that, for example, you see the convergent plate boundary, and you see on the Indian plate, at the north of the Indian plate, and on the eastern side in Indonesia and beyond, you see that the plate boundary is the convergent. Okay, convergent plate boundary, and the red lines, it indicates the ridges. So this is basically the mid-oceanic ridges. So this is your divergent plate boundaries, and these black lines, that is the transform plate boundaries. So in between these divergent plate boundaries are these ridges, mid-oceanic ridges. This is transform faults, you can see in the illustration. So absolute plate motions is mostly 5 centimeter per year, and relative plate motion around 5.5 centimeter. In case of this Indian plate, this is the movement around 5 to 5.5 centimeter per year. Now coming to this convergent plate boundary, you see convergent plate boundary may be of two types. One is continent-ocean plate boundary. Another is continent collision. One is continent-ocean subduction zone. That is an example is the Japan Island arc. That is in the left top. You see that oceanic crust is basically, it is compositionally, it is DInSAR. Okay, this is made of dominantly by silicon and this magnesium. So Si and Mas. So SIMA we call it. So this is oceanic crust is dense. So it is subducting slab, and on the right side it is the continental crust. Okay. So here you can see that the subducting slab is dehydrates, and there is partial melting, and then in the overlying mantle wedge there is partial melting, and then the mantle wedge feeds magma into it, and the volcano is taking place. Okay, so then in the bottom, if you see, this is continent collision. That is examples, is very important example is the Himalaya arc, and also European Alps. So here you see that both are continents, both the plates are the continental crust. So the one crust is going down, another crust is riding over this. Okay, and in the right side you see that is this Indian plate is shown here, and on the north you see there is the convergent plate boundary and subduction zone. Okay, and the red line, if you see at some places there are some red lines are there. So these are the locations of these recently occurring earthquakes, and thereafter related to that. And there are locations are given like the Bhuj 2001, then Kathmandu, then Quetta, then the number of locations you can see in the China. So all the locations of these recently occurring earthquakes. Okay. Now coming to the crustal deformation model and earthquake, that is the earthquake deformation model. So basically we understand this earthquake deformation cycle by two-stage model is to begin with. So here there are the two important stages. One stage is strong motion of earth crust and fault rupture, and this is essentially co-seismic deformation during the earthquake. Okay, this is stage one. And stage two is the slow motion, and here the strain is slowly getting accumulated, and there is elastic behavior of the earth crust in between the two or more earthquakes. So this is known as the interseismic deformation. So basically during the earthquake, this is the co-seismic deformation. Here the motion is very strong. Okay, the fault rupture takes place, earthquake occurs. Okay, this is co-seismic. And stage two is a slow motion and is a very long duration. Okay, slowly strain getting accumulated, and there is elastic behavior of the earth crust. Okay, and this is interseismic deformation. but this is extended further to 4-stage model of crustal deformation and earthquake, and this elastic rebound theory, it expanded into 4-stage conceptual model, and this model is also known as the earthquake deformation cycle. Now this initially there are the 2-staged this cycle, okay, that is the strong motion and the slow motion. Now there are 2 additional stages, that is one stage is pre-seismic and another stage is post-seismic. So pre-seismic and post-seismic slip or pre-seismic and post-seismic deformations, there are 2 additional stages to this initial 2-stage deformation to 4-stage earthquake deformation cycles. So pre-seismic is also known as foreshocks and the post-seismic is known as the aftershocks. Now, depending on the spatial and these temporal scales of the geological processes like earthquake and other processes, okay, there are different spaceborne geodetic techniques are available. Different kind of spaceborne geodetic techniques are recommended for studying these geological processes, for measuring and monitoring the geological processes. For example, there are different techniques are given like EDM, OB, this is electronic distance meter, GPS, SLR, satellite laser ranging, very long baseline interferometry. Okay, so you can see, for example, GPS, it can be applicable for a spatial scale of few tens of kilometers to hundreds of kilometers to even thousands of kilometers in terms of spatial extent or spatial coverage. And in terms of time scale, it can be applied even from 10 to the power 3 seconds to even up to you can see 10 to the power 8 to 10 to the power 9 seconds. So it's a very long time span. It can be used. This GPS technique can be used. Okay, but recently deformation interferometric SAR or DInSAR, that is our main interest of the today's lecture. Okay, the spaceborne deformation interferometric SAR technique or DInSAR or ScanSAR interferometry, they both are very, very useful technique for this measuring and monitoring this earthquake related deformation. So DInSAR, standard deformation interferometric SAR, is generally useful in terms of spatial scale from a few tens of kilometers to up to hundreds of kilometers. Okay, and in terms of time scale, you can say it is few days to few years only. And for ScanSAR interferometry, the time scale is more or less the same as in case of deformation interferometric SAR. It may be a little extended further, some tens of years. Like this, some few years to some up to 10 or little more years. And but what is more important in case of ScanSAR interferometry than the standard DInSAR is that it has a very large spatial coverage. So this technique can be applied for hundreds of kilometers, even up to thousands of kilometers, and it can be very, very useful for measuring the slow relative deformation over a very large areal extent. And in case of crustal deformation, okay, those are happening before the earthquake. Okay, these crustal deformation in general, it is a very slow deformation. So ScanSAR interferometry becomes very, very important nowadays to understand or to measure this very slow deformation, very slow crustal deformation, this between the earthquakes or before the earthquake. So ScanSAR interferometry is useful, and different kind of ScanSAR interferometry is available now. Some recent developments have occurred on ScanSAR interferometry, some better techniques, but than ScanSAR interferometry. Okay, so those kind of related to ScanSAR interferometry techniques are now used for this measuring this crustal deformation, where the deformation is taking place at a very slow rate and over a very large areal extent. Okay, and then DGNSS, that differential this global navigation satellite system. Okay, this is similar to this GPS, global positioning system. It is useful for these hundreds to thousands of kilometers, and for many years it can be applied. And also there are satellite-based gravity. This observation also is nowadays being used, and it can be used from these thousands of kilometers to even this spaceborne gravity technique. Okay, about this few years to tens of years. Now coming to the main your topic of today's lecture, that is the interferometric SAR and differential interferometric SAR. First, coming to the introduction. So synthetic aperture radar interferometry or InSAR is basically it is a technique of interference of SAR images basically we need two SAR images, and then we need to have interference of two SAR images for measuring the topography of the terrain, surface change, and most importantly for today's lecture, for measuring the surface deformation. Okay, so it is basically interference of two SAR images over the same area, which gives you the interferometric phase or the phase difference of the two synthetic aperture radar image, and this phase difference between these two images for each pixel, it can be used to measure and monitor the surface deformation. And this surface deformation can be related to an earthquake, or before the earthquake or after the earthquake, the crustal deformation before the earthquake or after the earthquake. So this is how this difference in interferometric SAR can be used for this kind of application. The principle of interferometric SAR is interference of phase. Okay, any SAR image or radar image has two components. There's amplitude component and the phase component. So for interferometry, what we need to do is interference of phase of two SAR images over the same area. Now after interference, what we get? We get the phase difference image or interprogram. Okay. Now from this phase difference image or the interprogram, this phase difference can be translated into the path difference between different SAR acquisitions. Okay, and from this phase difference, we can translate this phase difference to path difference, and from path difference, basically it can give you this terrain topography, and most importantly this displacement of the Earth surface. Okay, and in case of interferometric SAR, basically we get an interprogram or a differential interprogram. And what is that interprogram or differential interprogram? It is basically an image representation of pixel by pixel phase difference. In case of differential interprogram, it represents the phase difference due to the Earth surface deformation only. It's not due to topography of the surface. Okay, and in case of only interprogram, it gives you the phase difference due to this topographic elevation. Now in an interprogram, each phase cycle means how much? It is 2 pi radian phase difference. So in an interprogram, each phase cycle or 2 pi radian phase difference, it represents this thing, your unit of measure of an interprogram, or it is known as the unit of InSAR measurements. Okay, and it is known as a fringe. So InSAR fringe basically represents one phase cycle or 2 pi radian phase difference, and it is the unit of measure in an interprogram. So now coming to the next slide. So interferometric SAR or InSAR, there are different applications like topographic mapping. It can give you the very precise digital elevation model. Then from interferometric SAR, coherence can be used for a number of applications like land use landform mapping, environmental monitoring, coastal dynamics. All those things are possible. But on the right side, you see it is for land surface deformation, land surface displacement. Okay, and this land surface displacement, in bracket, you can see that it gives you land surface displacement in sub-centimeter level precision. From centimeter to sub-centimeter level precision, it gives you information due to an earthquake. Okay, what deformation takes place, deformation of the land surface or displacement of the land surface can be measured at sub-centimeter level. It can also be used for landslide monitoring, volcano, glacier, land subsidence like due to mining, due to groundwater pumping. Okay, so it can be used, but here in this particular lecture, this interferometry is very, very important for measuring the land surface displacement due to earthquake, during the time of earthquake, that is co-seismic deformation, and between the earthquakes, that means after an earthquake or before an earthquake, that is this interseismic land surface deformation can also be measured by this differential interferometric SAR technique. Now, this interferometric SAR, how we start with the SAR single loop complex image. So in a SAR single loop complex image, there are two components. One is the amplitude and the phase. And if you see this amplitude component of a SAR image, it represents the ground reflectivity. Okay, and also it also represents the speckle. That speckle is a multiplicative noise. Okay, so this is basically, sometimes speckle is also some kind of information, but it happens due to the interference of the return signal from these scatterers from inside a pixel. Okay, so that is why your brightness of the adjacent pixels having the similar kind of land cover will have different your brightness. So that gives you speckle effect. also known as the salt and pepper effect. Okay, so that is not important for today's class. So what is important is the phase information of the two SAR image. Okay, so or a single SAR image. So phase information of a single SAR image, it is the sum of two contributions. One is the internal contribution, phi internal, another is the phi travel, that is the round trip travel time of the radar signal. Okay, now phi internal component is random in nature, and this component is not known to us. So this component, unless we remove this component, we cannot use this deterministic component, that is the phi round trip this travel time, the phase due to the round trip travel of this radar this pulse. We cannot use that, so we need to remove that. So for this purpose we use two SAR image. Okay, we interfere two SAR image, and then we calculate the phase difference of the two SAR image. In the two SAR image we have both internal phase and the round trip travel phase, and we acquire these two SAR image in such a way that the internal phase of these two SAR image are very, very close to each other. So if you make one minus another, what will happen? In both the cases we will have the internal phase as well as the travel phase. Now we make one minus another, the internal phase is same for both the cases, and one will be nullified. And these both the internal phase terms will be nullified, one will nullify the other one. Then what will remain, that is your round trip travel path for one SAR image and the other SAR image. So this is the difference, phase difference due to the round trip travel distance of these two SAR image. Now on the right side you can see that this SAR signal is represented like any electromagnetic radiation. It is Z is equal to A exponent J phi, where A is amplitude and phi is the phase of this SAR signal. Now here from this you can get this amplitude of this SAR image, that is square root of A square plus B square, that's the real component square and the imaginary component square, and square root of that. And the phase is tan inverse B by A. And the phase is important to us because we need to do the interference of this phase information of two SAR image, and after interfering this phase information of two SAR image, we will get the phase difference. And based on this two SAR image, whether these two SAR image are acquired from the same platform or from different platforms, the SAR interferometry can be called as single pass interferometry or repeat pass interferometry. So for interferometry we need two SAR image, and these two SAR image can be acquired by the same platform like spacecraft. Okay, so now these two antenna can be placed on the same spacecraft at A1 and A2, that is the receiving antenna, and one antenna is transmitting the pulse. Now this phase difference from the single pass interferometry will be the phase difference of these two this SAR image for each pixel, this delta phi will be equal to 2 pi by lambda into del rho. And del rho is what? Del rho is the difference in this LOS distance or the slant range distance of the two image. In one case from A1 you are getting one image and that has a range of rho, and from A2 antenna you are getting another image and there is the range is rho plus del rho. So there is a path difference is del rho. Okay, so we get a phase difference delta phi is equal to 2 pi by lambda into del rho. Now in case of repeat pass, because these transmitting antenna are not same for both, because in both the cases this radar pulse is transmitted as well as received. Okay, so in this case this path difference is doubled up, so it is 2 del rho. So we are getting the phase difference delta phi is equal to 4 pi by lambda del rho. Now in case of interferometric SAR, so basically what we do, we calculate the phase difference between the two SAR image for the same point or for the these neighboring points. Now this phase difference of two neighboring points if we consider, then what happens? This is the phase difference due to the height of that your points and the horizontal distance of these 2 points. So if you consider two neighboring points, the horizontal distance from your radar antenna, okay, is not same for both. So there is a difference in the horizontal distance, and if they are not on the same elevation, there this vertical your difference is also there. So this total phase difference delta phi is basically it is equal to del phi horizontal plus del phi vertical. So but del phi horizontal is basically it happens or it comes into picture because of this difference in the baseline between the two this satellite, okay, S1 and S2. Okay, so this horizontal phase difference we need to subtract to get the vertical phase difference in case of digital elevation model generation. But our application is not just digital elevation model generation. Our application is for movement, land surface deformation. So here the delta phi, basically phase difference between two SAR images. So one SAR image we acquire before the earthquake, another SAR image we acquire after the earthquake. So one image before the earthquake, another image after the earthquake. Now we calculate the phase difference for each pixel. So for a particular pixel which is displaced due to the earthquake, okay, so there will be horizontal phase, there will be vertical phase, and there will be displacement or movement phase. Now from this total delta phi, we need to remove the horizontal phase because of the horizontal distance difference, and vertical phase because of the height of the target, okay, relative height difference of the these neighboring targets. So this del phi horizontal and del phi vertical we need to remove, and then we will get the del phi movement, which will represent the phase difference due to the movement of the earth surface due to an earthquake, or between the earthquakes the crustal deformation. So this will represent the phase difference due to that. Now, so we need to eliminate the horizontal phase and the topographic phase contribution for detection of the displacement component. So there are two methods for that. The first method, it is known as 3-pass interferometry or 4-pass interferometry, where we need to make a difference of two interprograms. It's made of 3 or 4 images. So where 2 images may be acquired before an event, and 2 images, out of that 1 image before the earthquake, before the event, and 1 image after the earthquake we need to acquire. So 2 images before the earthquake to get horizontal and vertical phase, and 2 images, 1 before the earthquake, 1 after the earthquake. From that we need to generate another interprogram, where we will have in this interprogram the phase difference, 1 before the earthquake, 1 after the earthquake. The phase difference will include, this is the horizontal phase, vertical phase, and the displacement phase along the radar line of sight. Okay, so now the interprogram which is generated using 2 images before the event, that will have both horizontal and vertical phase, and the interprogram which is generated using 1 image before the earthquake and 1 image after the earthquake, it will have 3 phase components, horizontal plus vertical plus displacement. Now what we need to do, we need to subtract this first interprogram from the second interprogram. Then what we will have, we will have the phase difference due to the displacement, okay, displacement due to the earthquake or this earthquake induced land surface deformation. Now in the second method, it is known as the 2-pass interferometry. We need only 2 images, 1 image before the earthquake and 1 image after the earthquake, but we need to have one reasonably good quality digital elevation model as per the sensitivity of this SAR data pair. Now from this 1 image before and after, we generate a differential interprogram, and from this differential interprogram we can map the land surface displacement, or the contours of the land surface displacement can be shown. Here in this differential interprogram, basically what we represent different phase cycles. Phase cycles means 2 pi radian phase differences, each phase cycle, and each phase cycle is known as a fringe. So each fringe in a differential interprogram basically represents lambda by 2. So lambda is this the what kind of radar data you are using, that is the lambda is the wavelength of the radar data. So it represents the lambda by 2 this displacement. Basically it is a line of sight displacement of the land surface, lambda by 2. For example, in case of C band, it is 5.6 centimeter, so lambda by 2 will be 2.8 centimeter. In case of L band, for example, it is 23 centimeter, so your lambda by 2 will be 11.5 centimeter, something like this. Okay. Now this is this 3-pass interferometry. We need to have one interprogram before the event, before the earthquake, and the dashed line shows that this data acquired after the earthquake. Now what I explained, that we have to generate one interprogram with A1, A2 dash, that is before earthquake and after earthquake, and another interprogram we have to generate both the data acquired before the earthquake, that is A1 and A2. Now interprogram from A1, A2 dash, and needs to be interprogram from A1, A2, that needs to be subtracted from the interprogram A1, A2 dash. Okay, A1, A2 dash has horizontal phase, vertical phase, and displacement phase, whereas A1, A2 interprogram has only horizontal and vertical phase. So A1, A2 interprogram needs to be subtracted from the other one. Then what will remain? It will give you the phase difference. Okay, there are some mathematical these derivations involved. There are some normalization of baseline is involved. finally what you will get, it is the delta pi is equal to 4 pi by lambda into delta rho. Okay, so in this interprogram, which is a difference interprogram, delta pi, the phase difference represents the phase difference due to the displacement. Now if the phase difference is one phase cycle, okay, or rather for each phase cycle, that means 2 pi radian phase difference, which is also known as a fringe. That means 2 pi radian is equal to how much? 2 pi radian is equal to this delta rho is equal to lambda by 2. Just put this 2 pi in place of delta pi, then what you will see that this delta rho will be lambda by 2. So that means one fringe or 2 pi radian phase difference in a difference interprogram represents lambda by 2 displacement. This displacement along the line of sight of the radar, that is along the range direction of the radar. Now this is the other method, which is relatively simplified method, where here you need two SAR image, one before and after, and you need a reasonably good quality DTM as well as the orbit data of the SAR data. So now from the master and slave image, we need to co-register these two images and we get a raw interprogram. And from this raw interprogram, we need to subtract the simulated interprogram. That simulated interprogram includes both horizontal phase and vertical phase. And how we get this both horizontal and vertical phase is like this. We have the orbit information and the DTM from the orbits. That means geometry of the this satellite from where these two images were acquired. So from this orbit information and from the this external DTM, we simulate the interprogram, and this interprogram includes both horizontal phase and the vertical phase. Now we need to subtract this simulated interprogram from the raw interprogram. Then what we'll get? We'll get the differential interprogram. So this differential interprogram means phase difference due to displacement of the surface. And after we geocode it, we'll get a geocoded differential interprogram that will show you the displacement over the land surface, okay, due to the earthquake. So difference interprogram if it is geocoded, then it will show on the DTM geometry. So you can compare with this thing here, actually what this displacement has happened and how much displacement has happened. Now, in case of difference in interferometric SAR, the precision of measure is very, very important. And this is the only technique which can give you this millimeter to centimeter level precision in a spatially continuous manner. Okay. So in case of GPS, you can get this similar kind of precision. Okay, but it is a point-based observation. For a particular point only, you will get this precision. But in case of difference in interferometric SAR, okay, you will get a fraction of lambda by 2 is the precision of measure. And what is lambda value? Lambda, depending on this thing, your different kind of radar data. It can be 3 centimeter in case of X band, 5.6 centimeter in case of C band, 10 centimeter in case of S band, and 23 centimeter in case of L band, and 60 centimeter in case of P band. Okay, so you can understand. So depending on the radar, this thing, your band, okay, the lambda has different kind of values. So if it is the C band, for example, this is lambda by 2 is equal to 2.8 centimeter or 28 millimeter, and the precision is a fraction of this lambda by 2. So it will be around few millimeters to few centimeters depending on the radar wavelength used. Actually, it is sigma displacement is equal to sigma phi, that is phase measurement uncertainty, divided by one complete phase cycle, that is sigma pi by 2 pi into lambda by 2. So that will give you the precision of measure, and it will come depending on the wavelength value, it will come few millimeters to few centimeters. Now coming to this spectacular, this thing, your the difference in interprogram, for the first time, this it was this observed from the difference in interferometric SAR technique. Okay, so co-seismic land surface displacement due to Lander's earthquake, and this is the first study using differential interferometric SAR. Okay, so Lander's earthquake that occurred 28 June 1992, and this French space agency, that is Kennes group, Massonet et al., they have for the first time they have generated difference interprogram to show this displacement due to the Lander's earthquake, and it was published in Nature. You can see that this displacement contours, it is oriented in the left side towards north, and on the right side it is towards south. So, and in between there is a white lines. Okay, these white lines are basically the ruptures or the fault plane which is exposed to the surface. Rupture is exposed to the surface, and this displacement in the left side it is towards north and the right side towards south. Basically, it is a dextral strike slip fault kind of displacement we can see, and on the right side it is the model differential interprogram. Okay, and Each phase cycle in this difference interprogram is 28 millimeter. Okay, then this, even simply counting the number of phase cycles or the fringes, you can have an estimate that how much displacement on the left side and right side, what is the relative displacement has taken place with respect to the rupture. Okay, so that is the strength of difference interferometry, and that was for the first time it was explored in 1993. Now there is another example like Eureka Valley. So here you can see the fringes, the composite interprograms is by stacking. So initially these two done by stacking of interprograms. Okay, so here you can see the concentric interprograms that show the subsidence of the hanging wall. Okay, it's up to 9.5 centimeter is the subsidence of the hanging wall. And this example, it is, you can see the North Ridge earthquake. So in this case, you see there's number of these phase cycles. Okay, so this number from these phase cycles, this on the basically the southern block, it is a thrust fault. Okay, the thrust fault is occurring to the north of the fringes. Okay, this co-seismic slip on the south dipping thrust. So this thrust plane is dipping towards south, and the southern block is riding over the this thrust plane towards north. And for that reason, what happens, the southern block is uplifted and there is a elevation change. Basically, elevation has been increased, elevation of the ground as much as 50 centimeters of the southern block. Now, if you see in case of bomb earthquake, okay, that is processed by us. So here you see that this earthquake occurred in 26th December 2003 and magnitude of the earthquake 6.5. And it was a very shallow earthquake, 4 to 5 kilometers. When the earthquake is very, very shallow, what will happen, these effects of the earthquake on the land surface will be also very high. So because of that, there are a lot of damage took place. In fact, 85% of the buildings were damaged. You can see on the right side, right top, that on the first photograph shows it is before the earthquake, and on the right side photograph is after the earthquake. You can see the almost everything has been damaged. Okay, 85% of the building were damaged, in fact, and there was 43,000 deaths. Okay, very large number. And here there is the rupture is about 20 kilometers long, and the fault is a strike slip fault. Okay, here you see in the on the left side, left top image is basically it is the this master image amplitude image. So it is the reflectivity of the earth surface in the SAR image, and the second image, that is the middle image, the is the coherence image. So this is the complex correlation coefficient of the two SAR image. It says that correlation coefficient is quite high, as the correlation coefficient before the earthquake, one data, and after the earthquake, another data of NBSAT data. It was used from European Space Agency data. So this complex correlation coefficient or coherence value is quite high. That is why it looks very bright. Okay. Then go down to the left bottom. You can see that the number of phase cycles or fringes, but there are many fringes are parallel fringes. So these parallel fringes happens to occur due to the flat earth surface. Okay, the horizontal phase. It is basically representing horizontal phase. So we need to remove that. So after removing this horizontal phase, what we get, it is at the middle bottom. You can see that is the fringes. Horizontal phases are not there. This essentially this is the fringes due to the displacement of the earthquake. Okay. Now if you study a little more, then you go to the right. Middle right, if you see that is the, it is shown in the red, orange, yellow, green, blue and indigo. So in this case you see that this the displacement is shown in different colors. Okay, so it is in this thing your meter, so it is around this how much this displacement it is shown here. Okay, and from this legend you can see this, it is tens of centimeters displacement has taken place. Now in the right bottom you can see the displacement vectors are this decomposed, and it is shown the how the displacement has taken place, and displacement vectors can be resolved. Now coming to the Nepal earthquake. Nepal earthquake occurred, that is a 7.8 magnitude earthquake. It's quite very large earthquake. Occurred 80 kilometers northwest of Kathmandu city. So you can see this is this location of the earthquake in the red star. Okay, and from the Kathmandu it is the distance is around 80 kilometers, and this earthquake occurred 25th April. Okay, and after this earthquake there are many aftershocks occurred. Okay, so that is of magnitude maybe 3, 4, 5, but there are some earthquakes even this greater than 6 magnitude earthquake occurred, like 6.3, 6.6, 6.7, and finally see there is a major aftershock occurred that is at very close to point C here. You can see the right illustration, so that is this another star is shown. So here this is the your major earthquake. It is, this one is what I have shown. It is 7.3. Okay, 7.3 magnitude moment major magnitude earthquake. Okay, and that is located 70 kilometer to the northeast of Kathmandu, and basically it is 140 kilometer east southeast of the main shock. Okay, and this occurred on 12 May. But interestingly, if you see, generally this is the earthquake is the strongest at the epicenter, and this is the earthquake epicenter. We have shown 7.8 magnitude earthquake epicenter is shown on the left side. Okay, near Gorkha. It is also known as, because of the locality, as a Gorkha earthquake. So here this damage of the earthquake and the deformation of the earthquake is not equally distributed with respect to the epicenter, whereas all the aftershocks are oriented in the east southeast direction to the east, and all the damages occurred on the eastern side only. So very interesting things happened. So all the aftershocks we can see on the eastern side. Okay, and this earthquake occurred basically at the main central thrust, very close to that, and it was a very shallow earthquake. So that is why damage was also very substantial due to that earthquake. Now, if you see the land surface deformation by the DInSAR technique, okay, see, this is the left side illustration. This is the L band. L band is basically from the Japanese satellite. ALOS 2 is the Japanese satellite, and L band means 23 centimeter wavelength band SAR image. It shows the deformation pattern of the main shock that happened on 25th April 2015. And here you can see there are two distinct patterns. The lower pattern is the uplift. There is an uplift of up to 165 centimeter. Okay, and the maximum uplift you can see it is very close to Kathmandu. Okay, and there is a subsidence. There is, you can see one elliptical pattern on the southern side. Okay, that is representing uplift, and here the maximum LOS, the subsidence. So in the southern side is uplift, and on the northern side is subsidence. Okay, so the southern side, this maximum uplift is 165 centimeter, and on the northern side, this your pattern is due to the subsidence of the land surface, and here the maximum subsidence is 60 centimeter. On the right side illustration, you see it is using the RadarSat-2 extended wide beam data. RadarSat-2 extended wide beam, but this is a fine beam data. This is a C-band data, so the wavelength is 5.6 centimeter, and the displacement pattern you see here, the more detailed displacement pattern we can get, because here the wavelength is shorter, 5.6 centimeter compared to 23 centimeter in case of ALOS 2 on the left side illustration. And here what we see the maximum line of sight land surface displacement is 170 centimeter or 1.7 meter displacement we can see here. Okay. Now, if you compare the displacement pattern due to main shock and the displacement pattern due to the major aftershock, that is on 12 May, 7.3 magnitude, and 7.8 magnitude main shock, that is on the left side. So you can compare that. In case of main shock, there is maximum uplift is 165 centimeter, and this aerial extent is quite large, and maximum LOS subsidence is 16 centimeter on the northern side. Whereas this, because of the major aftershock, okay, so that is 7.3 magnitude, and that occurred this on 25th, this 12th May. Okay, the left side it is 25th April. It's not 15th April. It is 25th April, and on the right side it is the major aftershock in 12th May. Okay, here you see there are two independent your fringe pattern. On the southern side, the number of fringes are more. So here it shows uplift of maximum uplift of 65 centimeter. Okay, and on the northern side, this patch represents the subsidence patch. Okay, so in the southern side is the this uplift patch up to 65 centimeter, and the northern side is the this subsidence patch. okay, up to 35. So this is the uplift and this is the subsidence. Here it is 65 centimeter line of sight and here it is 35 centimeter displacement. Now going to this your data pair. So in this case we have used allos to this strip map. This is the standard kind of data, interferometric SAR data. Okay, so here this aerial coverage is a little less. Okay, that is this area is covering very close to the Everest, the base camp, and near the snow avalanche site where the immediately after the earthquake snow avalanche occurred. So we got the data immediately after the earthquake. Very quickly we could process the data, and if you see in the left top, this is this amplitude image, and the glaciers are shown on that. And in the left bottom is the differential interprogram showing this land surface displacement due to the earthquake. Okay, and in this side, this is the Everest base camp is here. Okay, and we can see here there are some displacement. Okay, here the red areas, red to orange areas are the maximum displacement. So here we find that along certain lines, particularly these lines are aligned along the river valleys like Tamakoshi, Rolwaling Valley and Dudkoshi river valleys, the deformation is maximum. Okay, there is the peak ground acceleration, PGA is maximum. So because of that, there is a damage would be expected to be very, very high compared to the surrounding areas, very close to the Everest base camp. And these are basically, this deformation is controlled by the soft sediment as well as basically the weak structural planes, maybe perhaps responsible for more deformation. There are more stress can be propagated through this direction, and soft sediment, because of soft sediments, there is more shaking could take place. Now, if you compare with the DGNS observation, there is one DGNS observation we have from this very close to that the location point is named as the Dama, this point. Here we have the up component of the velocity due to the Nepal earthquake, and we see this is in fact there is a up component for that particular your station is around 15.6 centimeter. Okay, so all this displacement what we observe is not is uplift or this your subsidence, but there is a major component is from west to east. That is the horizontal component is a major component of this displacement is happening due to the earthquake. Now, for every earthquake, this rupture plane is very, very important, because all along the rupture, this maximum damage takes place. And from this rupture, in and around the rupture, we can calculate how the PGA value, peak ground acceleration, is varying from the rupture line, and accordingly we can assess the damage. So now here in this particular example, in this particular case, Nepal earthquake, there is rupture is not exposed to the surface. Rupture is buried under. So we need to have what is the possible locations of the location of the rupture. So that one way of doing that is by plotting these aftershocks, and based on the aftershocks, there are two possibilities. The rupture plane may be this either southern one or northern one based on the dashed lines. Now, if we use the differential interprogram, then it helps us to zero down to the possible rupture line, and based on that we estimated the PGA value to get the damage in and around the this Nepal earthquake location. So if you see the damage, the intensity of damage, if we see that is confined to mostly to the eastern side. Generally, the damage should take place in and around this epicenter, but in this case, only damage has taken mostly in the eastern part of the earthquake. And most interestingly, this damage took place on your foothill site of the earthquake. So the fault which is responsible for this earthquake, okay, it is related to the main central thrust. So it is observed that most of the damage took place on the footwall side. But in general, what happens, the maximum damage takes place on the hanging wall side. That is also very interesting in this particular case. Okay. This damage intensity map, you can see on the right side, the right top shows the damage intensity due to the main shock, and the right bottom shows the combined intensity from the main shock to the major aftershock, the damage intensity. And how this has been prepared, this is based on this MMI intensity value observed at different point locations, and it is crowdsourced data available from USGS. Then we have interpolated and prepared this damage intensity map for the Nepal region as well as for the Indian region, the south of this Nepal earthquake. And for Indian region, very interesting thing we have observed. In India, maximum damage occurs in patches. So in and around three locations, as if there are three lobes of this damage we have observed. One is Darbhanga, Betia and Balia location. Another is Jaidpur and Faizabad, that is in UP. And another is Jangipur and Bagdogra, that is in this West Bengal area. So there are these three lobes, one in and around UP, and another is mostly in the Bihar, another is West Bengal, and this your North Bengal, that is this Darjeeling, and it is also going up to this your Assam. This is the region of damage. Then why this damage took place in the three different locations as lobes at three places, that we attempted to study. So for that, what we have done, we have used the in situ parameters, in situ geological parameters, terrain parameters, okay, like it includes the rock types map, geomorphology, structural information, that includes the lineaments. Then what is the sediment thickness, what is the basement depth, all this information we have used. And most importantly, the PGA value we have estimated using this dependency intermediate SAR technique also. So based on all this information, we integrated all this information, and after that what we get is potential damage intensity map. And here what we observe, that here this geological structures like lineaments and faults, what we have shown in the upper two illustration. So these lineaments or faults plays a very important role for this damage in different lobes. Okay, and based on that, we observe that this on the right bottom, you see that the potential damage we can see in the three lobes. And if we compare with the actual this observed damage intensity map, it is quite agreeable with these two. These damage intensity maps are quite agreeable with each other. Now coming to your interseismic deformation, that is this geodynamics of this area. So basically we are studying the northwest part of the Himalaya. Okay, essentially this UP and Uttarakhand and the HP, this region. Okay, in this particular area, if you see what kind of observation that I will show in the next slides. So basically, for interseismic deformation related to this Himalayan region, what is observed, that this northern movement of the Indian plate, okay, and this intercontinental collision with the Eurasian plate, it causes, there are two kinds of deformation. Okay, basically there is one horizontal shortening, okay, and another is this vertical deformation, that is subtle topographic change from south to north of the Himalaya. So there are differential horizontal shortening and subtle elevation change. These together that highlight the location of the strain accumulation. So these two components of this crustal deformation, so interseismic crustal deformation rather. So we address this differential horizontal shortening by wide beam ScanSAR interferometry or similar technique like ScanSAR, like TopSAR. Okay, so this wide swath interferometric SAR technique, and this subtle topographic change, this is by differential interferometry only, but that is also we are doing by your time series deformation. Okay, like DInSAR or like different other techniques available like SBAS. Okay, so this can be done in many there are a number of these advanced differential interferometry SAR technique available nowadays. So what I'll show in this lecture, that differential interferometric phase profiling, if you do from north to south, then we can identify some of the strain accumulation sites. Okay. Now for that purpose, we have taken different north-south stretches, and then we have this calculated differential phase all along the south to north stretches, and then try to identify the locations of this your differential phase increase or difference phase decrease, and based on that, the strain accumulation sites have been identified. Then how we did it? Then for each stage, a number of difference in interferometric SAR data pairs for different years. For example, we have used allos 1 from 9 to 10, 10 to 11, and 7 to 8 different years. Similarly, we have used for 14, 15, 15, 16, 16, 17 for allos 2 data. Okay, 17, 18, like this. Now from south to north, we have first processed the difference interprogram, then we have constructed the differential phase profile, and based on this phase profile nature, we have identified the areas of strain accumulation. Now to identify this horizontal shortening, what we did this wide swath, your processing, and by this wide swath SCAMSAR interferometric processing, we have tried to identify the possible locations of this horizontal shortening. Here some of the published results we have shown, that is showing the east central Nepal and west central Nepal, this your observation from south to north. If you see in the west central Nepal, so InSAR based, basically NBSAT SAR InSAR based observation shows there is strain accumulation in and around main central thrust. Okay, and leveling based observation also, when it is compared with that, it shows the agreeable results. So if you see in the next slides, so if you see that similar kind of results by this your GPS leveling and interferometric SAR. So see in the left side, this second from top, InSAR based observation shows there is a vertical deformation is 5 to 10 millimeter per year, whereas horizontal this shortening, horizontal deformation is about 15 millimeter or more. That of course we are not getting from InSAR as shown by this your literature, that there is GPS based observation shows this horizontal displacement up to 15 centimeter, and we have also got similar kind of results. So around 22 centimeter is the displacement, which, and some places it is even more, but that includes both the horizontal and vertical. And on the right side you see that east central Nepal. So here the leveling, and in the left side InSAR, these two results are quite agreeable with each other. Okay. Now the similar kind of study was done for this east central Nepal also. So west central Nepal using NBSAT, and east central Nepal using allos. Now if these differential interprograms is compared, then you can see the strain accumulation is taking place more or less all along the MCT. And here in this particular study, it is shown that there is a LOS deformation is around 5 millimeter. It appears to be a little less. Okay, but because GPS and other kind of techniques, it shows up to 15 mm to 2 centimeter this your strain accumulation in and around this MCT. That is all this your lecture.